Hello, everyone, and welcome to our lesson on coordinate geometry. Today, we're going to dive into the fundamental concepts of straight lines in two dimensions. We'll be focusing on the equations of straight lines. By the end of this lesson, you will be able to define the gradient of a straight line, calculate it from 2 points, and understand the different forms of a line's equation. These are our main goals for today. We'll build on these concepts to understand parallel and perpendicular lines and how to find where lines intersect. Let's begin with the most basic property of a straight line, its steepness. We'll start with the concepts of gradient and intercepts. The gradient of a straight line is a measure of how steep it is. A larger number for the gradient means a steeper line. The gradient tells us how the y value changes as the x value increases. First, let's consider a positive gradient. As we move from left to right, so as x increases, the line goes upwards. This means the y value also increases. We say this line has a positive gradient. Next, a negative gradient. Here, as x increases, the line goes downwards. This means the y value decreases. This line has a negative gradient. Finally, what if the line is perfectly flat or horizontal? As x increases, the y value doesn't change at all. It remains constant. In this case, the gradient is 0. So, the gradient describes the direction and steepness of a line. But how do we calculate it? We need a precise formula. The gradient, which we often denote with the letter m, is defined as the change in the y-coordinate divided by the change in the x-coordinate. You might have heard this called rise over run. To calculate this, we need two distinct points on the line. Let's say we have 2 points, which we'll call x and y1 and x2, y2. The change in x, or the run, is the difference between the x-coordinates, x2 minus x1. The change in y, or the rise, is the difference between the y-coordinates, y2 minus yn. This gives us our key formula for the gradient. The gradient m is equal to y2 minus y1 divided by x2 minus x1. This formula is fundamental to everything we'll do with straight lines. Let's work through an example to see this in action. Let's find the gradient of the line that connects the points 3, 2, and 5, -4. First, we need to label our points. It doesn't matter which one we call point 1 and which one we call point 2, as long as we are consistent. Let's set x and y1 to be 3, 2, and x2, y2 to be 5, -4. Now, we substitute these values into our gradient formula. So m equals y2, which is -4, minus yn, which is 2, all divided by x2, which is 5, minus x1, which is 3. Now we just need to simplify the expression. The numerator -4 minus 2 is -6. The denominator 5 minus 3 is 2. So the gradient is -6 divided by 2, which equals -3. The gradient of this line is -3. A common source of error is mixing up the coordinates. Let's look at a few incorrect attempts to see what can go wrong. Consider finding the gradient for the points 3, -2 and -4, 7. Here's one attempt. The calculation is m equals -9/7. This is actually correct. Let's check. If x and y1 is -4, 7, and x2, y2 is 3, -2, then y2 minus yn is -2 minus 7 equals 9, and x2 minus x1 is 3 4 equals 7, so m equals -9/7. Let's try it the other way. If x and yn is 3, -2, and x2, y2 is -4, 7, then y2 minus yn is 7, -2 equals 9, and x2 minus x1 is -4, -3, -7. So m equals -7 equals -7, so it works both ways. Now look at this second attempt. Here, the student used y2 from one point, but y1 from a different problem. Or perhaps miscopied the point 3 2 as 3, 2. The y-coordinates should be 7 and -2. The calculation should be 7 minus -2, not 7 2. This is a common mistake, so always double-check your points. In this third solution, the student has mixed up the x and y coordinates. They've calculated y1 minus x1, or y2 minus x2, which is not the formula for gradient. Remember, it's always change in y over change in x, or rise over run. Be careful to keep your y values in the numerator and your x values in the denominator. Great. We've now covered how to define and calculate the gradient of a line. Let's move on to intercepts. In this scene, we'll learn about intercepts and a very useful form for the equation of a line. Our goals are to find the x and y intercepts and to use the gradient intercept form of a linear equation. The intercepts are the points where the line crosses the coordinate axes. The x-intercept is where the line crosses the horizontal x-axis. At every point on the x-axis, the y-coordinate is 0. So to find the x-intercept, we set y equal to 0 in the line's equation. Similarly, the y-intercept is where the line crosses the vertical y-axis. For any point on the y-axis, the x-coordinate is 0. So to find the y-intercept, we set x equal to 0. Let's find the intercepts for a specific line. Consider the equation 2x plus 3y minus 6 equals 0. Let's find its intercepts. First, for the x-intercept, we set y equal to 0. Substituting y equals 0, we get 2x plus 3 times 0 minus 6 equals 0. This simplifies to 2x minus 6 equals 0. Adding 6 to both sides gives 2x equals 6. Dividing by 2, we find x equals 3. So the x-intercept is the point 3, 0. Now for the y-intercept, we set x equal to 0. Substituting x equals 0, we get 2 times 0 plus 3y minus 6 equals 0. This simplifies to 3y minus 6 equals 0. Adding 6 to both sides gives 3y equals 6. Dividing by 3, we find y equals 2. So the y-intercept is the point 0, 2. The y-intercept is particularly important because it appears in a very common form of a line's equation. This is called the gradient-intercept form, y equals mx plus c. It's incredibly useful because it tells you the gradient and the y-intercept just by looking at it. In this form, m is the gradient of the line and c is the y-coordinate of the y-intercept. So the y-intercept point is 0, c. Interestingly, while the concept is universal, the letters used can change. In the US and some other countries, you'll often see y equals mx plus b. Other variations like y equals ax plus b or y equals kxn are used elsewhere. It's a good reminder that mathematical notation isn't always a single international language, but the underlying concepts are the same. Let's use this form to build an equation. Suppose we need to find the equation of a line with a gradient of 4 and a y-intercept of -3. We have m and c, so we can directly use the gradient-intercept form. Here, m is 4 and c is -3. Plugging these into y equals mx plus c, we get y equals 4x plus -3, which simplifies to y equals 4x minus 3. That's the equation of our line. Sometimes you'll be asked to write the equation in a different format. For example, we might need the form ax plus b plus d equals 0. To get this, we just move all the terms to one side. Subtracting 4x from both sides and adding 3 to both sides gives us -4x plus y plus 3 equals 0. Excellent. We've now seen how to find intercepts and how to use the gradient-intercept form, which is a powerful tool for describing straight lines. Welcome back. In this scene, we'll explore two other common forms for the equation of a straight line. Our objectives are to work with the general form and the point gradient form of a line's equation. First, let's look at the general form, which we just saw, ax plus b plus c equals 0. In this form, all terms are on one side of the equation. A key skill is to be able to find the gradient and y-intercept when the equation is given in this form. To do that, we rearrange it into the gradient-intercept form, y equals mx plus c. Let's try an example. We'll find the gradient and y-intercept of the line 3x plus 4y plus 6 equals 0. Our goal is to isolate y on one side of the equation. First, we'll move the x term and the constant term to the right side. We subtract 3x and 6 from both sides, which gives us 4y equals -3x minus 6. Now to get y by itself, we divide the entire equation by 4. Dividing both sides by 4, we get y equals -3/4 x minus 6 over 4. We can simplify the fraction 6 over 4 to 3 over 2. Now the equation is in the form y equals mx plus c. By comparing our result to y equals mx plus c, we can see that the gradient m is -3/4 and the y-intercept c is -3 q. Now, what if we don't know the y-intercept, but we know the gradient and some other point on the line? For this, we have another very useful form. This is the point gradient form. It allows us to write the equation of a line if we know its gradient m and the coordinates of any single point x and y on the line. This formula comes directly from the gradient formula. If we have a known point x and y win and any other general point x, y on the line, the gradient is m equals y minus y win, x minus x win. If we multiply both sides by x minus x win, we get the point gradient form. Let's see that again. We start with the definition of gradient between a specific point y and a general point x, y. Multiplying both sides by the denominator gives us the point gradient form. Let's use it in an example. Let's find the equation for a line with gradient 2 that passes through the point 3, 5. Here we have m equals 2x3 and y equals 5. We substitute these values directly into the point gradient formula. Y minus y becomes y minus 5, and m times x minus x1 becomes 2 times x minus 3. So the equation is y minus 5 equals 2x minus 3. Often, this is a perfectly acceptable final answer, unless you're asked to put it in another form. Let's try a slightly more complex problem where we have to find the gradient first. Find the equation of the line connecting the points -1, 1 and 3, -7. Step 1 is to find the gradient using our gradient formula. Let's take x and y1 as -1, 1 and x2, y2 as 3, -7. The gradient m is -7 minus 1 divided by 3 minus -1, which is -8 divided by 4. So the gradient is -2. Step 2 is to use the point gradient form. We can use either of the 2 points. Let's use the point -1, 1. Substituting m equals 2x minus 1 and y equals 1 into the formula, we get y minus 1 minus 2 to x minus 1. This simplifies to y minus 1 equals minus 2 of x plus 1. And that's our equation. What if we had used the other point, 3 minus 7? Let's check. We would get y minus 7 minus 2x minus 3, which is y plus 7 minus 2x minus 3. If you expand both equations, you'll find they are identical. Both are correct. So now we have 3 powerful forms for the equation of a line. Let's see how they apply to parallel and perpendicular lines. In this scene, we'll investigate the special relationships between parallel and perpendicular lines. Our goals are to understand the gradient rules for parallel and perpendicular lines, and then use those rules to find their equations. Let's start with parallel lines. Parallel lines are lines that never intersect, no matter how far they are extended. Think of them as train tracks. For this to be true, they must have the exact same steepness. This leads to a very simple rule. Parallel lines have the same gradient. If the gradient of the first line is m1 and the gradient of the second line is m2, then for the lines to be parallel, m1 must equal m2. Let's apply this to a problem. We need to find the equation of a line that is parallel to the line 2x plus y plus 6 equals 0 and passes through the point 2, 5. First, we need to find the gradient of the given line. We rearrange 2x plus y plus 6 equals 0 into the form y equals mx plus c. Subtracting 2x and 6 from both sides gives y minus 2x minus 6. From this, we can see the gradient is -2. Since our new line is parallel, it must have the same gradient. So the line we're looking for has a gradient of -2 and passes through the point 2, 5. We can use the point gradient form, y minus yn equals m of x minus x1. Substituting our values, we get y minus 5 equals -2x minus 2. This is the equation of our parallel line. Now, let's move on to perpendicular lines. Perpendicular lines are lines that intersect at a right angle, 90 degrees. The relationship between their gradients is a bit more complex. If 2 lines are perpendicular, the product of their gradients is -1. Another way to say this is that one gradient is the negative reciprocal of the other. So if you know m1, you can find m2 by flipping it and changing the sign. Let's visualize why this is true. Imagine a line L1 with gradient m. We can think of this as a rise of m for a run of 1. Now, if we rotate this entire picture by 90 degrees, the line L1 becomes a new perpendicular line L2. The original run of 1 becomes a vertical drop of -1, and the original rise of m becomes a horizontal run of m. So the gradient of this new perpendicular line L2 is its new rise over its new run, which is -1 divided by m. This gives us the rule m2 equals -1 m1. Let's use this rule in an example. We want to find the equation of a line that is perpendicular to y equals 5x plus 2 and goes through the point 1, 6. First, identify the gradient of the original line. The line is y equals 5x plus 2. This is already in gradient intercept form, so we can see that its gradient, which we'll call m1, is 5. Next, find the gradient of the perpendicular line. The gradient of our new line, m2, must be the negative reciprocal of 5, so m2 is -1 over 5. Finally, use the point gradient form with the new gradient and the given point. We have a gradient of -1/5 and a point 1/6. Using the point gradient form, we get y minus 6 equals -1/5 times x minus 1. This is the equation of the perpendicular line. We have now mastered the relationships for parallel and perpendicular lines. In our final scene, we'll see how to find where lines cross. Welcome to our final scene. Here, we'll learn how to find the point of intersection of 2 lines and apply our knowledge to a modeling problem. Our objectives are to find where 2 lines intersect and to apply the concept of gradient to a real-world model. Let's start with the intersection of 2 lines. Unless 2 lines are parallel or identical, they will intersect at exactly one point. This point of intersection is special because it's the only point that lies on both lines. This means its xy coordinates must satisfy both equations simultaneously. Therefore, to find the coordinates of the intersection point, we need to solve the two equations as a system of simultaneous equations. Let's work through an example. Let's find the intersection point of the lines y equals 3x plus 2 and y equals x plus 4. At the point of intersection, the y-coordinate must be the same for both equations. This means we can set the expressions for y equal to each other. Since y equals 3x plus 2 and y also equals x plus 4, it must be true that 3x plus 2 is equal to x plus 4. Now we have an equation with only one variable, x, which we can solve. To solve for x, let's get the x terms on one side and the constants on the other. Subtracting x from both sides gives 2x plus 2 equals 4. Then subtracting 2 from both sides gives 2x equals 2. Finally, dividing by 2, we find that x equals 1. We've found the x-coordinate of the intersection. To find the y-coordinate, we substitute this x value back into either of the original equations. Let's use the second equation, y equals x plus 4. Substituting x equals 1, we get y equals 1 plus 4, which is 5, so the y-coordinate is 5. The point of intersection is 1, 5. Let's try one more example, this time with the equations in general form. Let's find the intersection of x plus 2y equals 5 and x minus 2y minus 3. For this system, the elimination method works well. Notice that we have a plus 2y in the first equation and a minus 2y in the second. If we add the two equations together, the y terms will cancel out. Adding the left sides gives x plus 2y minus 2y, which is 2x. Adding the right sides gives 5 plus minus 3, which is 2. So we have 2x equals 2, which means x equals 1. Now substitute x equals 1 into the first equation to find y. We get 1 plus 2y equals 5. Subtracting 1 gives 2y equals 4. Dividing by 2 gives y equals 2. So the point of intersection is 1, 2. Finally, let's see how gradient can be used in a simple model. Imagine a mountain is modeled as a cone. Its height is 8,800 meters, and the width of its base is 24,000 meters. We want to find the gradient of its slope. The gradient is rise over run. The rise is the height of the mountain, so the rise is 8,800 meters. The run is the horizontal distance from the center of the base to the edge. The base width is the full diameter, so the run is half of that. The run is the radius of the cone's base, which is half the diameter. So the run is 24,000 divided by 2, which is 12,000 meters. Now we can calculate the gradient. The gradient is the rise divided by the run, which is 8,800 divided by 12,000. This simplifies to 88 over 120, or 11 over 15, which is approximately 0.733. This gives us a measure of the mountain's steepness. And that brings us to the end of our lesson. We've covered the core concepts of straight-line equations, from calculating gradients and intercepts to understanding different forms of the equation, analyzing parallel and perpendicular lines, and finding their points of intersection. These are foundational skills in mathematics that you will use in many other areas. Thank you for your attention.